The variance and the standard deviation are sensitive to the units that you measure something in, or to scaling. So if your scale is in feet, you'll get a different number for variance and standard deviation than if you rescale to inches or to kilometers or something else like that. The formulas for how they depend are like this. We really like the standard deviation because if you have to scale your data by multiplying all your x's by some number, the standard deviation itself scales up by the same amount. Variance, unfortunately, scales by a lot more than that, by the square of your conversion factor. In the next video, this video, I want to show you where these two formulas come from and why it's the case. This video is a little bit math heavy, so you can get away, I think, with just memorizing the formulas, but I'd prefer that you actually play along with this, maybe even work it out along with me, so that you can understand where these formulas come from, because I'd much rather you understand it than to memorize it. So here we go. We got to start off with the definition of variance. The variance of some number is the difference of each observation, the difference from the mean for each observation I, not just the difference but the squared difference, and then we want to calculate the average squared difference. So we're going to add up all these values and divide by the number of observations. That's just our formula for the variance. If we were going to spread this thing out, we would have x1 minus x bar squared, our first observation's squared difference from the mean. We would do that for our second observation, and so on and so forth all the way until our very last observation. We would add up all of those n terms and then divide by n. Okay, so that's the definition for variance. Now what if we took our data, our x's, and we multiplied each of them by 12, or by some constant a? Well, then I want to know what is the variance of this new number, ax. So everywhere that I see an x in this original formula, I need to replace it with ax. Now along the way, so I'm going to do that here for all of the xi's, I'm going to have to do it here for the average. And so let me just take a little sidebar and think about how the average responds to rescaling. Now, I can just denote the average of x like this, expected value of x. That is just x1 plus x2 all the way through xn, and we're dividing by the total number. So what happens if I were to rescale all of those x's? Well, then I would have my rescaled first observation plus my rescaled second observation all the way through to my very last, now nicely rescaled observation. And then we divide by our n terms. And if we do that, we can pull out an a from all of these terms in the numerator, leaving us with x1 plus x2 plus xn, all divided by n. But just a moment, that's what this is. And so this formula is just a times the expected value of x. Okay, so just to put it into this x bar notation, if we have some number, average of x, but I want to know what is the average of ax, so what is the average of that whole thing, we can just say it's a times the original average of x. Let me put this again into just plain English. You got a class average. Let's say the class average was at 50. Pretty bad. The professor goes, I don't want to fail my entire class. So how about this? How about I take everybody's score and I multiply it by 1.10. No, better yet, I multiply it by 2. So take everybody's score, multiply it by 2. Well, then what do you think is going to happen to the new average? Well, the old average was 50. So now, after I multiply everybody's score by 2, my new average becomes 100. It's 2 times the old average. That's all I'm trying to get at here. When we're rescaling our x's, our averages just get rescaled exactly proportionately. All right, so that was my sidebar. Let's go back to variance now. We want to know what is the variance of our rescaled data, this ax. So everywhere that I saw an x before, I got to replace it with ax because my data set is now changed. It's been updated, multiplying by 2 or by 12 or something. So let's take all of these terms, and everywhere I saw an xi, that's now going to be an axi. And x bar becomes ax bar. And that was squared. And then we divide by n. Okay. So what does this mean? Let's separate this thing out. Let's do like this. So we have ax1 minus ax bar. So it's still the difference between our data and the average. It's just everything's been rescaled now. And I want to square that difference. And I'm going to do that for my second observation too. All the way down, and we're dividing by n. Now how can I simplify this? This is getting gnarly here. I need to expand this squared term. So I need to like FOIL it, if you remember that from high school. So what do? You take the first term and you square it. Minus 2 times ab. And then the last term squared. This is just A1. We got to do that for A2 and A3 and all the way through. So we have A squared x sub 2 minus 2ax sub 2 ax bar plus a2x bar squared. Dot, dot, dot. All of it dividing by n. Again, gnarly, but we need to simplify because this thing, it's way too complicated. Let me clean some space on my my little board here, and then we'll continue. Okay, so I've cleaned off my whiteboard. Let's continue working. Switch colors too, just to try to keep this stuff separate. So we're still trying to simplify this, that the variance of ax is now equal to this gnarly thing. I'm going to multiply this out and then try to combine some terms. So we have a squared x1 squared. That was this first term. Now let's do this second term. So we have minus 2 a squared, because we have a here and a there, x1 times x bar. All right, so that was our second term. And now we just copy our third term. Okay, so that was this first term in brackets. We have a similar term for our second, all the way through to our third, fourth, down to our nth. All the way down to n. Notice that a squared shows up in each of my terms here. So I can pull it out. So I have a squared x1 squared minus 2x1 x bar, and then pull out the a squared, leaving me with x bar squared. So I can pull out that a squared from this term. I would also pull it out from here and from all the other similar terms. So now we're working with the second observation. So our little subscript changes to a 2. And I forgot that I was supposed to be dividing by n. So let's make sure I have that. Divide this whole thing by n. Take that whole thing. Divide by n. Can't forget that. I have an a squared term now in each of, like in front of each of these bracketed terms. So I can keep pulling that out. So now I have a squared. I've got this term. My second term. And so forth. Add them all up. Divide by n. Man, this is just, this doesn't look any simpler, does it? Well, it will in just one moment. You see, it turns out that this entire thing, everything but the a squared, we actually already saw before. Let me clean my plate one more time and show you where we've actually seen this before. So this term here, all the way through to the dividing by n, turns out that's this guy in disguise. Let's just expand these squared terms too. This first term is, we got a FOIL again. We have x1 minus 2ab, and the last term squared. We got to do that for the second term. And so forth. And we got to divide by n. But notice, this green term is equal to that. Plus dot, dot, dot. And there's our dot, dot, dot. And then we divide by n. And there's our dividing by n. So we can just substitute this, which is equal to this, which is equal to that, which is equal to, we could just substitute v of x right here. So, all right. So I think we're done, actually. We just proved that the variance of ax is equal to, it was a whole bunch of stuff, and we expanded and we FOILed and we gathered terms and then we pulled out terms twice. And then it was equal to this gnarly thing, but that gnarly thing was equal to this, which was equal to that, which is equal to that, which is equal to v of x. So we have a squared v of x, which was actually what we were trying to prove. So a long way to go for a very simple formula. But at least you've now seen it derived. It wasn't just pulled out from thin air. It is actually just an intense application of algebra. We can do the same thing for the standard deviation. But that one's a whole lot easier. I'll do that in the tiny amount of space I have remaining. Let me just switch colors one more time. We'll go purple. Okay, so how do I derive this? The standard deviation of ax is equal to a, the standard deviation of x. All right, well, if I just take the square root of the variance, that's the standard deviation of ax. And if I take the square root of the left side, I got to take the square root of the right side. Now the square root of a squared is just a, leaving me with a times the square root of the variance of x, which we know is just the standard deviation of x. And so we've just proven what we wanted to prove. So the hard one was the variance. All right. Thanks for watching.